class, we are now on 9.2a. This is formal charge and Lewis structures for polyatomic ions. So in chapter 5, we introduce polyatomic ions as groups of atoms with an overall charge. The distribution of these charges across the ions affects many of their chemical properties. Now that we have a better understanding of covalent bonding, let's look at the structures of 8 common polyatomic ions. Most of these ions follow the octet rule, but 2 ions, sulfate, right here, sulfate, and phosphate, have expanded octets. I lost my place. Notice that each polyatomic ion has at least one atom with a positive or negative charge. These charges are formal charges. They allow us to locate charge sites within a molecule or polyatomic ion. Formal charges are not a perfect indicator of the charge on an atom, but they're a good tool for keeping track of the overall charge of a molecule or ion. In this lesson, we will see how to calculate formal charges and how to use formal charges when drawing Lewis structures for polyatomic ions. So why do we care about this? We care about this because as you start trying to draw out structures, you could possibly draw out several. And the charges and how to calculate formal charges and where the charges are will allow you to find the one that is the most stable out of them. So that's where we're going to go with this, because a lot of these can be drawn, not all of them, but some of them can be drawn different ways, and the charges can be moved onto different things. Like, for instance, we see this charge, but we can also move these bonds or electrons around and have a charge on this one. You can also move the bonds around and have a charge on this one. So which out of those 3 is the right compound? And that's what we're going to look at. When we don't know that until we know the formal charges on the compounds. So formal charge is an estimate of the total electron charge around the bonded atoms. Formal charge assumes that atoms share electrons evenly. Since 2 atoms share 2 electrons, each covalent bond contributes a charge equivalent of 1 electron. We calculate formal charges using this equation. Formal charge equals the number of valence electrons. So formal charge equals the number of valence electrons in the neutral atom minus the number of covalent bonds minus the number of unshared electrons. And you do this for every single atom. You don't do it for an overall compound. You use this for every atom that's in a compound to get the formal charge on it. Excuse me. For example, here's hydroxide. The hydroxide ion has a charge of 1 based on this Lewis structure. Does the negative charge lie on the oxygen atom or on the hydrogen atom? So when we see this, we only see that has a charge here, but we don't see where that charge is on the compound. This is going to actually let us go into the compound and figure out where it is. And that does determine, if we have several compounds with several different charges, which one tends to be the one that we would use. That is the most stable out of all of them. So we calculate the formal charge on each atom, and you do that for every atom. So in this case, we have a formal charge. Excuse me, all of a sudden my throat starts acting up right when I start recording. So let's take a look at this. Valence electrons in neutral atoms. So for hydrogen, we have 1. We have a number of covalent bonds. We have 1. And we have no unshared electrons. So it's 0. So the overall charge on this is 0. So when you start writing this out, you can write a 0 here. Oxygen. We have 6 valence electrons. We have number of covalent bonds. We have 1. And we have number of unshared electrons. 2, 4, 6, 6. So this ends up being -1. So we don't tend to necessarily, we write the negative here, so it's indicating the overall compound, but it's actually on the oxygen. And you could have seen this even without doing it because, well, I mean, I'm not saying, once you started doing this, you would have caught that there's a 6 here. So that means that there is, an oxygen atom has an excess of electrons and has an overall charge of -1. So when we draw the Lewis structure of hydroxide, we show the minus charge adjacent to the oxygen. And this are one things that this is the thing I want to point out. When you start seeing an oxygen with 1 bond and 6 electrons, you'll start doing this over and over again. It has a negative charge. And I will show you here. Let's go back. So you see here's a single bond, 6, that's a negative. When you have an oxygen that has 2 bonds and 2 pairs of electrons, that's a neutral. So you can see there's a trend. You see this has got 0 because there's nothing here, but you see that when you have it with 6 around it, it's neutral. It's a negative charge. So and it happens over and over. You can see that there's a trend with that. Double bond 0, single bond a negative charge. Excuse me, I apologize. I don't know where this all of a sudden came from. Formal charges are a powerful tool and especially important in biological chemistry. For example, oxygen atoms commonly have formal charges. When covalently bonded, a neutral oxygen atom has 2 bonds and 4 unshared electrons. If the oxygen atom has 3 bonds, it will have a formal charge of a plus. On the other hand, if an oxygen atom has only 1 bond, it will have a formal charge of a negative. Negative 1. The formal charges on nitrogen have a similar trend. Nitrogen commonly has a formal charge of negative 1 or 0 or a plus, depending on the number of covalent bonds. So what I just covered is here, you can see there's a single bond, 6 allowed, it's a negative. It takes 2 bonds or a double bond in some cases, but it has 2 bonds, 2 lone pair, it's a 0. If it has 3 bonds and a lone pair, it's a plus. And if you look at nitrogen, nitrogen has 2 bonds, 2 lone pair, it's a negative. 3 bonds and a lone pair, it's a neutral, and 4 bonds, it's positive. Okay, so let's look at an example. Automotive bags contain sodium azide. The Lewis structure of I know I'm going to say this wrong. An azide ion. Sorry, it's combined on mine. Without charges is shown, azide. Calculate the formal charge on each atom in the structure. What is the overall charge of this ion? So let's begin with the central atom. Because nitrogen is in group 5A, we know that neutral nitrogen has 5 valence electrons. This nitrogen atom has 4 covalent bonds and a 0 unshared electrons. Therefore, the formal charge of this atom is a plus. And you can see that here. We have 5 valence electrons, 4 bonds, 0 lone pair. It's a plus. And there's the plus right there. Now we go to the left. A neutral atom, nitrogen atom, has 5 valence electrons. And this nitrogen atom has 2 covalent bonds and 4 unshared electrons. Therefore, the formal charge is 1. The right nitrogen atom is identical to the left, so you have a negative and a negative on here. And that, so if you look at it, this cancels out this one, but it still leaves 1 with a negative charge. Okay, so drawing Lewis structures for polyatomic ions is similar to drawing Lewis structures for neutral molecules. By the way, in my video, which I haven't posted yet because I'm recording these, it also works for polyatomic ions that are in the, again, row 1 and row 2, which really is just row 2. But if you just have to do one extra step, and it'll help you with polyatomic ions as well. Okay, so how drawing Lewis structures for polyatomic ions is similar to drawing Lewis structures for neutral molecules. We must consider the charge of the ion when we determine the number of valence electrons present. If an ion has a negative charge, it means there are extra electrons present. For example, how many valence electrons are present in a hydroxide ion? We know that hydroxide has a formula of an O and an H, HO minus. The oxygen atom has 6 valence electrons, and the hydrogen atom has 1 valence electrons. Where's that at? Oh, here it is. I'm like, what happened to my slide? Okay. The oxygen atom has 6 valence electrons, and the hydrogen atom has 1. The charge, the negative 1, means that 1 additional electron is present. This gives us a total of 8 valence electrons. I always remove these things because I don't like that they do this step by step. Sometimes there's like 30 of these and it annoys me on one slide. So I didn't know what happened to it. Let's look at an example. Draw a Lewis structure for the nitrite ion. Show all non-zero formal charges. To solve this problem, we follow the steps laid out in earlier. We add up the electrons. We can determine that nitrogen has 5, oxygen has 6. Because there's a negative charge, we know that we have to add 1 more additional. And that's where people mess up. So make sure if you're dealing with a polyatomic ion and it's got a negative, you add 1 more. Therefore, it has a total of 18 valence electrons. Frame the structure. So in this case, oxygens are, nitrogen's on the left of oxygen, so nitrogen's going to be in the middle. In this case, it's not always that way, but for this example of what it tells you is nitrite ion, that's what it's going to be. Fill the octets of the outer atoms first, and placing electrons around each oxygen using 16 of 18. Fill the octet on the central atom, and we have 2 remaining electrons, which we can place on the central atom. This leaves the nitrogen 2 electrons short of a filled octet. In order to fill the octet, we must move 2 electrons from one of the oxygen atoms to form a double bond between the nitrogen and oxygen. Finally, we can show the formal charges as drawn. The oxygen atom on the left has a formal charge of -1. We indicate this with a minus charge to give the final answer. So remember when I told you that if there's a double bond, oxygen has 2 double bonds, 2, 4, 6, 8, 10. Yeah, that's not right. I have to look this one over. This does not look right. Okay, they did it again. I didn't catch it when I first looked at this. These electrons need to disappear. They're not there. So let's see, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. So this would disappear a pair of electrons on this one. Count it up. There should be 18. So somebody made a mistake. And even though I kept staring at this prior to this, I never even caught it till right now. This has to go. So there's an extra pair of electrons. There should only be 2 pairs. So in fact, if you want to erase these, there should be 2 pairs and the 2 pair. And that's it. Not, this is way more than it should be. It's not correct. Okay, so sometimes it's possible to draw more than one Lewis structure. In these cases, we can use formal charges to identify the best structure. For example, look at the structure of phosgene, which is COCl2, a highly toxic gas that's used as a chemical weapon in World War I. We draw Lewis structure for this compound by allowing the steps we just outlined. Placing the carbon atom in the center and filling the octets of the peripheral atoms, we get a structure like thiazone, which, like this one. Gosh, I'm sorry, my words on here, I can't understand my own writing. That's awful. I just made up my own compound. Now we need to fill the octet on the central atom. We could do this with either a double bond to the oxygen or with a double bond to chlorine, which is more correct. This is where knowing formal charges come in. You want something that has no charges. If it doesn't have charges, it's actually more stable than anything that has a charge. Well, this is why we do the formal charges, to find, in most cases, you can make different, you can draw up different structures. And sometimes you can have several structures. And you've got to figure out which is the one that would exist. So to answer this question, it's helpful to include the formal charges. As a general rule, the best Lewis structures are those that minimize the charge values or have 0 values for all the atoms. The best structure for phosgene has a double bond to oxygen and single bonds to chlorines because all atoms have formal charge of 0. So that's where you see the charges. Yes, these cancel each other out, but they're actually not as stable as something that has 0 charges all around. Okay, so remember formal charges, the equation, you use this for every atom in a compound. Valence electrons in the neutral atom minus number of covalent bonds minus number of unshared electrons. So we show the formal charges on each oxygen or nitrogen. So if you have something, you should show the charge on it because that also indicates it's a polyatomic ion that you're dealing with. If you don't, then you're assuming it's a neutral compound, and if it's not, then it's actually incorrect. So you have to show the charges, or you have to show a charge somewhere. You know, sometimes they'll put it on the side, but the best way is to put it near where the compound has that charge. Okay, so here we can, you see this is a negative, this is a 0, this is a plus, and if you use this equation, you should be able to determine where this comes from. Okay, again, nitrogen, show the formal charges on each nitrogen. So I ended up, we covered this earlier, but you can see there's -1, +1, -1. If it's symmetrical on 1, then it's going to be the same, but I just copy and pasted this so you can see how to do the equation. Draw the Lewis structure for the nitrite ion. Yes, we've already done this, but this is good that you have a slide that's empty. Try to see if you can do this on your own and then take a look at it to see what it looks like. And this is actually the correct one compared to what is in your slides, which I did not catch. So the other one, if you remember, had an extra pair here. Should not. Oxygen always has either 2 pairs and 2 bonds or 3 pairs and 1 bond. So this is the correct one. Disregard the one that's in the practice slides. What is the formal charge on the circled atom? Because I've already told you that in general, if you start doing these enough, you won't even have to do the formal charges on some of these atoms because you see them so much. This one is a -1. In this Lewis structure, which atom has a non-zero formal charge? So in this case, you would have to go through each each atom and determine it. I did not do this one on purpose so that, yes, you know what the answer is, but you should still go through to see. Obviously it tells you that this must be 0 and this must be 0, so it has to be this one. And because you have 1 single bond and 6, there's a negative charge here. Again, though, because you know the answers, you should go through and make sure that when you do the work, it matches what you know. Which of these is the best structure for carbonate? So again, we want ones with the least charges to them. So when you start getting something that has charges on all of them, you want to, and you have options, you want to completely disregard. You want to, that's not stable. They're just not stable. You want ones, so if you start looking, you can see which ones would tend to be the one that, excuse me, I can't clear my throat. That tends to be the one that you want. And let me explain why this one would be. Because this one has a double bond, it has a non-formal, it has a 0 charge here, and these are separate. It has a negative charge and a negative charge. Less charges is what you want. This is too many charges all around. This isn't right because when you have a double bond and lone pairs, it doesn't have a negative charge on it. So this isn't correct. So they're actually making up things that don't exist. But this is where you have to go through and make sure that you see that. And you see this has 3 charges, where this only has 2. So less charges is what the compound is that you want to deal with. Based on the formal charges, which of these is the best Lewis structure for hydrozoic acid? I'm going to give you the answer. I did not work it out. So this way you can see why this one, if you work out both of these, and then you can see why this one was picked over the other one. Based on formal charges, again, structure, which is the best for thiocyanate? Again, I didn't do these on purpose, but I'm going to give you the answer. Assign all formal charges to this ion. What is the overall charge of this ion? So if it has charges, then you add those all up, and that's going to give you the overall. Again, I didn't do this one on purpose. If any of these don't make sense to you, we can always work on them. Please let